Well, hello and welcome to today's show. Today's show is on a different background that I've really never used before. I've had it for a long time, just never used it. This is for my main channel type stuff. Now, this is on a band sealer. Now, you may not know what a band sealer is or why you would use it, but it just seals plastic bags closed, and it takes up a heck of a lot of space. The one I got takes up about 3 feet of space on the bench, so I wish I hadn't bought it now. The cheapest option you have, we see them typically all over everywhere. They're just like, they look like a big stapler, right? And so they mash down. You turn the heat up on one end and you mash it down so many seconds. And by knowing what heat setting you have and what thickness of plastics and type of plastics, how long you need to have to hold that down. That's the simplest thing. You get them from $6 to $20. I have another one here that is a lot smaller if you're doing a lot of smaller type things like beads or maybe individual cookies, and you're packing for a Girl Scout outing or something like that, and you're just making a little snack and you're individually packaging a couple of cookies or beads. Maybe your wife or girlfriend makes earrings and stuff out of beads and necklaces. It's a way to just seal the bags down. They're about 1/4 of the price as band sealer. And the idea at that price, you buy a couple of them. One of them craps out in the middle of your job. You throw it to the side and put the other one up there. There's also other options very similar to the stapler type, where they hinge and come down. But these come down like this and they're foot operated. That's a nice thing. They're about half of the price of a band sealer. And they even make one that's about the same price as the kind of alligator jaws I just described. And what it doesn't have a conveyor. It's just the motor head portion of it with the print head. Now, in this first segment, it's the longest part of it. The rest of the more interesting stuff is kind of short toward the back where we get to see it work, but we had to talk about what we're doing. I decided to modify this thing, put a timer circuit on it so that it would run and cool down naturally. This first segment is the long part. Next segment we'll see the actual relays work, proof of concept that's doing what I told it to. And then the last part, we'll look at my very rough hand sketch and I'll talk you through it. Again, it's not 100% accurate on the sketch, but my part is what I had to do when I had to take it out of the brain, put it on the paper so I could see if this is going to work. So let's go from there. Well, I hadn't really intended to do a video on this subject. We're going to do one because it might help someone. Who knows, you might have a little cookie operation going on and whatnot. This is a pretty typical Chinese-made band sealer, and we have a certain number of parts you see over there in the cigar boxes. We have the belts. These are on the end by the roller. Then we have the ribbons, which are also kind of flat belts. They're the high temperature part. Let's see how the system works. As you can see, the little bright shiny brass, I call those irons. That's where they get heated up at. The side that's got the holes through there, air is on the back side of it. I don't know if you can see till we go around there, but there's just a fan blows across those. Those are the cooling section. And this section down here is really not very useful per se because of the way the print head works. It's not ink, it's an embossing type mechanical head. These things are very difficult to work with. To change the lot number or date or whatnot with this type of primitive equipment, you have to totally remove this screw in its entirety, loosen this one by the pressure knob, pull this piece completely off. Then we have to go under here, take that screw out, pull the pulleys off the end of the shafts. Then you have enough slack in the white V-belt like things. These guys, those are green. These are a little bit wider color, but you pull that off, and then you can reach to replace. This is the one that comes mounted on it. My advice to you is to leave it alone because this does a good job in making a nice seal. It's nice and wide. The print head itself is just a pain in the butt to work with because it has a lot of individual little letters, and you have to put them in and try to hold them, and maybe you can tape them in, but you have to change them every single day or every single lot number, every single expiration date. The kit that comes with it does not have enough to do any of that stuff with, so you just end up angry and frustrated. You can write EXP and LOT and whatever the other one is, expired lot, MFG, but you don't have enough numbers to go around. So it's just a pain in the butt. Plus, you'd have to change them every single time. So to do that little head, a little wheel, is about 2 hours worth of work Pretty much. So I would just leave, first piece of advice is just leave the standard head that mounts on it. I think China is smart enough to realize that nobody's really going to use the print head per se. Just leave the ribbon on it, be fine. Now, the way the system works, we have a counter, 3 switches. We have a little variable resistor, which is used to set the belt speed here, and it also sets everything else because it's just mechanically attached. Everything's mechanically attached to the same drive motor, so they work in unison. We have the temperature controller here. Obviously the fan switch, I wish it were blue for cool, and the orange, I wish that was red for heat, and I wish the button up here that is red for power, I wish it was maybe yellow or green or some other color. So the basic idea is to start the unit, to do a banding to seal. We come around to the edge, and you see there's a real finger squasher right here between that mechanical set. I'm sure it will mash it completely. But we don't do that because we don't want to go to emergency room. It has a little bracket that puts on here. I could show it to you, but it's as useless as it could be. I've heard some people review these things saying everything was fine till a couple of weeks ago. It started making an awful noise. No one can help. Well, probably this thing, as weak as it is just rubbing that little pulley. I found it makes noise, so I just took it off. It doesn't really help much. Anyway, I just run a slow belt speed to make this work. Now, to see it work, the way we would do, we would turn the unit on. We would then turn the heater on, and I'm going to have the fan on because it's going to just keep blowing cool air through here. Now we'll see that it's beginning to heat up. I'm going to go to 185C. We're going to go over here. We have a little sail switch up underneath this area, which clicks every time a bag comes through the process this way. So that's what it is. Now what I wanted to do is, before I modified this, I had an issue. These little what I call them, little bands, little ribbon belts, they would get awfully hot on this heater, this set of irons here. We would try to cool it down over here, but if we just turn the unit off, it's going to let all that heat cook right on that one little section of 2 different belts. And we do have extra belts over here in the cigar box, but we don't want to use them if we can help it, because just like your car never waits till you have a weekend off or 3-day weekend off or something like that to crap out on you. It quits in the middle of having to be somewhere. So I want to keep this running as much as possible. So you have a choice. You can just turn it off and let it cook, or you can come up here and remember, let's turn the heater off, right? And leave the fan on, leave the power on, and come back in, say 10 minutes or so. Hopefully you won't forget and this thing just won't go miles and miles and miles and all that. What I've done is I've made a modification to it, so if I turn this off in 10 minutes, and I may have the timer back there temporarily set much shorter, but it will just continue to run. No heat, no power switch on, just the fan. And as you notice, the controller's not working. The way I modified it was leaving as much intact as possible. There we go. See how it stopped? You hear how it stopped? So that would be the effectiveness of a cool down cycle, and I don't have to worry about it or fiddle with it. So if you're interested in this, I'll show you how I modified the circuit, and maybe... Hey, appreciate you watching. Do me a favor, if you will, subscribe to the channel, either the YouTube or the Rumble channel, which this appears in. And if you can, check the notification bell or settings to make sure that you get notified when new videos are posted. Appreciate it. Let's go look and watch the relays actually work. Now we have the heat running, we have the power on. We're going to pretend that we're at end of cycle, turn it off. Turn off the heat. You see relay number 1 goes dark, which fires the timer. You see the rightmost light come on. We're going to turn off the power. That's when we don't need it anymore, because we have relay number 2, which is the left relay. We have it latched on for the duration of the cool down cycle. When the cool down cycle ends, you'll see the left light on the H3Y come on, and you'll hear the machine stop. Now these timers are not true Omrons, and they're not very expensive, and they're also not very good, but they'll do okay for this, because if you're looking at $9 or $10 versus $100, anywhere from $60 to $120 a timer, I can live with a little inaccuracy. I'm not doing anything except just turning the belt off once I have cooled down, which I figured is about 10 minutes. 8 minutes would do just about as well. All right, now this is not a schematic for this thing by any means. It's just something that I started penciling out when I wanted to make sure I had the right contacts, the right logic, that sort of thing, see how much it would have. Had to relocate one of the built-in pieces. I really didn't touch that much, just turned it sideways and put it on a piece of DIN rail, mounted the other 3 relays. And this is how I got it out of the brain onto the page and into the box. So let's take a look at this next talk through section here where we look at the hand sketch. Now let's look at the left panel. And here we have the left panel. Just to remember what we had, we called this device right here the factory device. This is what's in the machine, and it was held down by 2 screws. In fact, I recycled them here and here. And I used what is called DIN rail, a little piece of DIN rail, and I had to cut it out of a longer piece because I see a lot of combos where you get a little piece of DIN rail and then 2 relays, but they're only long enough for 2 relays, and I have 4 across here. This is an octagon base right here. It's like an old tube type, although I don't know anybody calls them tube types anymore. But this has an old octagon base to it, that this multifunction device that's made just for this device and others like it. Then we have a relay, a control relay number 1, and a control relay number 2, and a timer in the middle. And this timer is an H3Y, and it's a 110 volt coil. All these are 110 volt coils because we're in America. And this has a 10-minute maximum time. So that's where we have it. Now let's go back and look at this other screen, and we'll look at the hand sketch. All right, now here's the wiring diagram. I got my mouse showing up on the screen. Now it's a little rough. It wasn't ever intended to be released, but I thought, well, you can see how the thought process works this way. And here we have the blue wire and the red wire coming in off the side of the box where we plug in the external cord. And because this is Chinese, not American right here, I don't really know which one is which without putting a voltmeter to it. So I checked ground to blue and got voltage, and I went ground to red and got nothing, or essentially nothing, which means that's the neutral. Now, it is illegal in the United States to disconnect and switch a circuit based on the return line or the neutral line, because that would pass hot wire and power through all of the machine, and the only thing that would be breaking is the path back to ground, which can be a human being, which we don't want that. It is, however, legal to break both of them. When can you break a neutral? Only if you break all of the hot wires. So here, that's where we are. So looking back at this left panel, we see the relays as we have it set up. I didn't want to change anything on the original. I don't really have a wiring diagram. I'm guessing what's in here. Obviously, we have the resistive control that works that little, either that FET back here that's hidden in this box somewhere, or it's a triac where we can change the gate voltage, but that's how we get our variable voltage. But it also appears to have a couple of other devices in here, maybe a bridge, and we have some relays. And one of the things you see taken off here is the motor wire. So we know that when we fire this up, before we modified it, that's what turns on the motor. And the motor runs off of this switched unit based upon the little green wires that go up to the variable resistor. And we know we have power going down to it. Now, I could have taken off of that. We see the purple wires. The purple wires go over to the counter, so we know we've got power in here. Well, we're just not going to mess with this, but we want to think about it in terms of this picture right here and the operation. How is it going to work? Go back to the little sketch. If I just leave it on, these contacts that I have right here do absolutely nothing, right? If this is on, we're passing power, doesn't matter what these do. If this is off, it's off. So I have to have some way of putting power from this side of the switch to the load side of the switch, because that load side of the switch goes to the heat switch and it goes to the cooling fan switch. It also comes down here somewhere in that octagon base, that tube base type device down there. And I don't want to mess with any of this part. And I'm really not messing with any of the inherent circuitry as it's built. But if I looked at the device, I see that the cooling switch is nothing more than power going to a fan. All right, it may not actually tap off where I show you, but it's the AC power going across a switch like a light switch, that rocker switch, to turn the little fan on. And we know that our heat switch does the same thing, and it turns on the controller, the heater controller. And it actually turns it on by turning this stuff on down here. But however it's done off the base of this, I don't really care. I just need to know when the heat switch is on, it's turning on a relay. Now let's go back to that left-hand side again. So here we are. We have the unit running. This is the first stage of it. We now have the unit running. The heat switch is on. We see that little red light. That tells me that the heaters are working. There are 2 of them, one in each iron, and it's running right there. As soon as we turn the heat switch off, we go to that next stage. This turns off and it starts a timer, because we are powering the timer and it's starting its sequence based upon whenever we turn the power off. Well, how are we turning the power off? We're turning this thing on. Well, let's go back to that little sketch. The terminology that we often use, you'll see, this is normally called a normally open contact, and it's depicted by having a gap in between here, right? So this is a contact, this is a contact. It's a double pole because we have two of them, right? And they look like this down here. The relays look like this. This configuration is called a form C, meaning that you have a common and you have one normally closed and one normally open. And the normally closed is indicated by that little slash to it. So I know I won't ever power past the power switch unless I'm pulling magnetically that coil of relay number 2, because that's when I close these contacts. If I never turn the switch off, it doesn't matter what this stuff does, it's just going to pass straight through as a normal operation. But if I turn off the heat, right, I want to leave the fan running, and I want the motor to keep turning the little conveyor belt so I don't burn the belt. All right, so when this switch opens up, there's no more power going through that coil, and it relaxes. Well, how do I control the timer? And what does the timer do? Well, we go back to that screenshot over here. We see the timer is on and this is off. So T1 is on, R1 is off. So that means I need the normally closed contact from R1 to turn on the timer. Go back once more to the drawing. All right, got a little sketch over here. Now when I look at this sketch, I see there's my coil and it's across 13 and 14, and we can see 13 and 14, and down here in the sketch it says from the heat switch, the load side. This is the load side, this is the line side. So I'm pulling off of the load side of that switch to feed R1. So as long as that switch is on and we're heating, R1 is energized right here. That gives us that red light. Well, I'm going across 9 and 1. Obviously, that's my switch contacts. Go down here, 9 and 1. That tells me I'm using that normally closed. So when I'm not energizing R1, it relaxes, and 1 and 9 operate as a switch. So that feeds the timer, and we see it coming off of, if we chase the wire down, we got a black wire coming in, or in this case it's blue. I wired it actually in black because I had more black wire than blue wire, and it comes around here from 12, and it's all the same wire, and we come right around here, and we roll around here, and we come up to one side, which would be number 1 down here, and they jump over to number 1 on the timer. Same thing, they got exactly the same pin outs. So I'm taking power in on 1, and I'm taking it off of 9. So when we turn off R1, we're passing power to this right here, to the number 9. It comes right around here, and number 9 then feeds 14 of the timer. And if we look at the timer, that's what I've got drawn out over here. So that when I turn off the heat switch, I turn off R1, and I turn on the timer. How does the timer work? Well, it's about the most simple timer that you can find. It's down here. I got a little picture of it. So this represents power. When I turn power on, it stays on. And the output on the normally closed contact stays relaxed until we time out of that time period that I have set for 10 minutes. At the end of 10 minutes, it latches that relay and it turns off the normally closed by turning on the normally open. And it stays in that condition the whole time. Look back at this picture over here. So when this one relaxed, because we turned the heat switch off, we turned on the timer, and the timer's power indicator shows that we have power, and it stays here until the end of that time period, in which case you'll see this light come on, which is the output, and that light is also a normally closed or a not, so it is not timer, turns off the relay number 2. Let's go look, see how that works. Back over to the diagram. Let me get my mouse in the right page. Click that. So when this goes dead, it relaxes the normally closed contact, which passes power to the timer. The timer now keeps this output on its 1 to 9 closed until the end of the time period that we see right here. It keeps it closed for this time period. What are we doing with the power we're passing through here? We go right up this wire into 14, which happens to be this wire on R2. We chase it right around here. Okay, it's the number 9 wire, comes into number 14, or the coil on relay 2, or that leftmost relay, and the other side just goes back to neutral. Now what else are we doing up here? When relay 2 closes, it closes these contacts. So as soon as we turn off that switch, timer turns on and it automatically starts that time period, but it latches these two contacts closed, bypassing that switch. So we just have to remember, turn this one off first, the heat switch off first, then we turn off the power switch, and this is totally in control. The second relay is totally in control of running the device because we didn't change any of the normal wiring. Go back to that other screen. So here we're not timed out yet, so we haven't turned on the output. So this being turned on and that not being turned off, right at this point leaves R2 operating. Now let me move that one out of the way, and now we see when the timer times out. This is off because we have no heat switch. This turns on power. It timed out. The relay times up, which actually cut the power to relay number 2, and we turned off the unit. Does that make sense? Here we are again. Turn the heat switch off, which drops the power to R1. This relay's light goes out. It fires the timer, turning that right light on. That's how we know that the timer's powered. It starts this time frame right here. And so the output time does not change until time is expired, in which case it latches. Normally closed opens because it's magnetically pulled down, and then the normally open turns on. So right here I have the normally closed. So as soon as we turn it off, power is running through this, running through R2, latching this relay. The light comes on, which closes these contacts. Once they're closed, I can then open that switch, and it's very, very fast. So I just have to do this one first, then that one. And at the end of that time period, it cuts off. So does that make sense to you? It's very simple. Now, the one drawback to this very simple design that I have here is, so whenever you first plug the unit in, if the power glitches out, it will start the mechanical belt for that 10-minute period, where depending on the timer, exhausting 10 minutes to unlatch that relay. Otherwise, it's going straight through whether it's turned on or not. So there is a cute little sticker that I put up here, and I'll show you a picture of it to remind my distractible self that if the power comes off, whenever I plug it in for the first time, like if I'm moving the box from one side of the bench to the other, that I need to keep my fingers away from the pinchy part. Because here's a picture of what the Chinese tell us. It says, carefully pinch hand, or whatever it says. And we actually want to carefully not pinch the hand. So I'll probably make me another one just because I can and put it on the side of the unit. So what do you think about that? Does that make sense to you? It's something I could do, and I did it, and I need some content, so I show you how this is all done. Appreciate you watching this segment. Bonus time. We have some bonus content here, if I can get through that with this splitter of a headache I've got going on. But this answers a question that we didn't bring up from the first, but of course you know I know the answer because I've already done this. So we're going to look at some bonus feature that maybe might help some folks more than others. If you don't want to watch it, just go ahead and turn it off. But if you want to see how to verify which relay types you use for something like this, stick around because we're kicking it off right now. All right, we got some bonus action today. We're going to look at this nameplate which says the power is 750 watts, which means if we were to figure our current on that at 120 volts, that would be about 6¼ amps. Now if we come around to this side and we look at our relays, we remember that our relays are good for 6 amp. So we're going to have an old school lesson coming up here. If you care to watch, we're going to learn how to read an analog meter. Are you ready? Let's go. Now, traditionally, an analog meter, now this one's probably older than you are. This says we're looking at ACA, which is AC amps, and we have 300, 150, 60, 15, and 6. And because we anticipate having more than 6 amps on there, 6¼ we're going to see what we actually draw to see if we need to replace the relay with a different type, which of course, yeah, I got that too. But we're going to see what I saw and what we look at. Okay, the way the meter sits, you see we were sitting at 0. I could adjust that mechanically with that screw right there, but that's going to be close enough for government work. And what we're going to do is we're going to look at this scale right there, 60 amp. See that 60 amp bottom arc, 15 on the bottom, 6 on the top, because 6 will work for 60. Because if we go back up to the top, we see we have 6 and 60. So where we see 60, if we're on the 6 scale there, that knob is turned to the 6 is going to be 6.0. So we come down here and look, and we see the A, not the V, the A, that bottom arc, and it says 6. So that will be 6 amps, 5 amps, 4 amps, 3 amps, 2 amps, 1 amps, and 0 amps. All right, now I could dial this in just a little bit right here by turning this to get that needle exactly flat, and I may do that for the next cut. All right, we have done our mechanical adjustment and we see that it is setting at 0. And remember, on the upper scale on the arc where it says 60, that's going to be our 6 amps. Now traditionally, if we're not sure, we will put it on the next highest scale, which would be 15 amps, and we'll turn the unit on and see what happens. Here we have our power right here. Turn on power. Let's see if we're in the ballpark. Barely even moved. So let's go ahead and turn on our heater. You see we don't have anything on the controller. We're going to go ahead and push this, turn on, and we'll see as it comes up to speed, we'll see the meter kick. And we're on 15 amps if it will stay focused. And we see we're below 5 amps. So let's go ahead and turn our knob to 6. And this is what we have on the heat mode. And we see up here at the top, we can see it's heating up. The present value is 42, 43 degrees C, so it's heating up pretty good. But what does it say we have? Now this is going through this relay because we're also going through this relay and the switch simultaneously. Now if I turn the switch off, we'll have all of our current going through this little black pair of wires right here. So what we want to do is give that a shot and watch the meter down here, because now we're going to have the switch turned off, so the only path to power the machine is going to be through the relay contacts, and we want to see no more than 6 amps. So let's go down and see what we got. We're less than 4 amps. Now the heater, what you just saw there, the heater kicked off. Now it kicked back on, and you see we are below 4 amps. Let's call it 4 amps because it's going to be easier to work with, because we're going to do some calculation here in a little bit. Now I'm doing this video on the day later, in the middle of the day when there's not many people pulling power out here in the country, and we can see we're right at 4 amps, just a little bit below. So our voltage is going to be fairly stable, because your voltage doesn't stay the same the whole time that you have power connected. It goes up and it goes down as the load and demand hits. See, we've already seen that go down a little bit. That can also be that we're heating up a little bit, but it's still pretty regular to what we had a while ago. Well, here I have the island that the sealer is sitting on, and I have probes in the bottom receptacle of the duplex. We have a digital meter. Now these are easier to read. We have the heat on, and we're at 119.6 volt. We'll listen for it to kick off. And it drops, actually it doesn't drop, it rises to 121.0, because we are seeing some loss of voltage in the line themselves that feed from the panel to the other panel, to the outside box, all the way to the inlet where we're bringing the power in. But you see what we got going here. Your voltage is not uniform. It's going to be a function of the current pulled. Now let's look at this one last time. We see what we've done here. We're actually running the heater with the heat switch, because we're using relay number 2 to latch the power so that we can turn the motor. If we turn off the orange switch, that's the heater switch, we'll be just turning the motor and the rest of it. But this is the abnormal situation that we wouldn't do if we used our shutdown procedure. And we can see we were headed to 185C and we're at 183, and we can look down here and see even as we heat up, we're not getting above 6 amps. So I don't think we need to change that relay, but I'll show you how you can look at a relay and the base and determine whether or not it's going to be a 10 amp or below 10 amp relay and base. Well, all right, if you made it this far into this particular video, you must have actually been interested in how control relays work and this kind of stuff goes. Now, it ended up a lot longer than I wanted, about twice as long, and I really could have made this into a second video. but I can't always be sure if people saw the second video. It may just come up because of an algorithm or something like that. Providing that you click like and subscribe to all this stuff, hit the notification bell, and you'll see the new videos when they come out. And I also thought it would be good if you saw it all at the same day before you went too far, because it might have an effect on your relay selection, because we go through and try to get it some abnormal situations just to make sure we've thought of everything. Plus, I thought some of you may never have seen an analog meter. It might be good for that as well, so I just packed it in one gigantic long video. The choice is always yours whether or not you want to watch, but if you will, it really does help if you'll like the channel and subscribe to it, hit the notification bell, that kind of thing. So let's get to what we had, because we asked the question, how do you know if your relays are suitable for either the 6 amp smaller output or are able to do the 10 amp? Well, let's look. Here we go. Well, you can look at the devices right there, and if you have the devices, I've got this so you can notice something particular about it. But basically, it's written on the relay, so you can always read the relay and see what its voltage is, what its pinouts are, and that sort of good jazz. But you'll notice something in this picture. This one is the 10 amp setup. This one is the 6 amp setup, and you'll notice something right here on the coil connection. These are vertical, these are horizontal, and I don't know if it's just smaller because this is 6 amp and this is 10 amp, so we have bigger contacts. But one thing you'll be certain to find is on the coil on a 10 amp relay, like an iDeck that I would prefer to use, you'll find it sitting vertical and the other's horizontal. The contacts are horizontal. And the difference is the quality of a good iDeck relay. An iDeck relay with an LED in it, you're probably going to find for 20 bucks a piece just for the relay without the base to go with it. And you have to get the matching base, as you see here. This is sold as an Omron, and it's only $5 for the relay and about $5 for the socket here, the DIN rail socket. And this together runs only about 10 bucks, where you're talking probably 30 bucks or so for a good quality iDeck. There are some off brands, some other brands that I don't recognize, made in China, and they're significantly cheaper, but they're still more expensive than the 6 amp jobs. If you'll read the reviews and see what people say, sometimes they say the contacts don't hold up, or maybe they burned them, or maybe they have something a little bit wrong in their relay logic, and so they're chattering a little bit. Can't always tell. But a good iDeck relay, you'll notice they'll be yellow and you'll pay for it. And just like the relay that we had, that we talked about as far as the genuine Omron quality type of timer that's going to work all the way down in the low section of the dial, good quality timer is probably going to be about 114, 120 bucks. Now you might find some for 60 or 80 bucks. I don't know if that got that much markup in them or not, but it is what it is. And you take a risk anytime you don't buy from a reputable source. If you're buying off Amazon or one of the Chinese websites, you may not get a genuine article, although it looks like it. Now, I did one more thing for you, and I've keyed up the page here. What I've done is resketched the original working drawing a little bit. It's a little crooked and that kind of thing, but it's just a little bit better version, because I want to point out this stuff is how the original unit was wired, with the exception of this guy put in here. This is, again, the octagon base and where the wires go. This is a pot or a variable resistor. The drive unit comes off of 5 and 6. The counter has a switch. I actually show it with 2 wires. We see down here it actually has 3, but as far as I can tell, we're really only using the VCC and OP for operational. Ground, I'm not really sure what it does, but we have this pretty well much exactly like the wires run, and that's why it's a little more messy looking, but it helps understand how they actually go within the system. And all I did is add my control circuitry over here, and of course this relay right here. So I can tell I did not disrupt any of the original design. I just kind of piggybacked on them. Here we still have our wiring as it was done. I just made a little note of how the timer was connected. The relays that I had shown you were top view down, so I wanted to point out that this is where the LED is in this corner, because typically when you look at a relay and you flip it over, the relay looking at it like we saw in that first picture is actually how you would read those terminals in the wiring diagram. I actually had it flipped the other way around based upon the bases, because I'm planning on plugging it directly in and I want to go from there to the other. Now they're mirrored on each side, so it really shouldn't matter, except for the fact if you're crossing your signals on your switches, that could be a problem. Let's look at that one more time. You see, we actually see that 12 and 9 are here, 14 and 13 are here, and when we look at this, we see that 14 from the bottom is on the opposite side. So my wiring diagram that I provided you is showing you from the top, so it matches the bases right here. From the top, matching the bases right here, and I even gave you this added little note right here. Here are some relays. They're what I looked at. You don't have to use them. The thing is, if you needed a 10 amp contact, after you get it wired, you're not just going to be able to buy a relay and pop it in there. You'll have to buy a relay and a base and just wire that base up just like the other one and then plug it in. Because as engineers, we would not want to be able to put a 6 amp relay rated contact in a 10 amp rated socket, because if we needed a 10 amp, we must have needed a 10 amp. That's why we put it there. And that's just it. I appreciate you watching. I know this is long, but again, I just want to repeat that by showing you the first part of it, I got thinking later, maybe it might help somebody else's unit, because it said it was 750 watts. I didn't want you to think that I didn't know to use a 10 amp relay if it needed it, if I was over 6 amps. But I knew I was under 6 amps because I checked it. But I thought maybe that really ought to be part of this project before we got to it. All right, so appreciate you. Again, I just want to hit you one more time with that request. If you like the content, if it's something that interests you, if you'll subscribe to the channel that you see this and hit the notification bell, it helps with the algorithms, it helps with the viewers. And I have such a wide range of stuff to show. It's not necessarily a theme-sponsored page particularly. It's a life kind of random thing that we go through. Appreciate you. Have a great week. Stay safe, everybody, and thank you very much.